Jnanam Paramam Dhyayam. Knowledge is supreme.
Okay, so let us continue our study of K spectrum. So what we did, I will just recall briefly that we have defined a map Vk from ideals in the polynomial ring Kx1 to xn to the power set of k power n. Any ideal A goes to Vk of A. Vk of A is by definition all those points in k power n, so that all polynomials in the ideal A vanish at that point. Now actually this I could have taken the radical ideals, not only all ideals, but I can restrict these to only radical ideals. So I will write here R. R is for radical ideals, because ideal and its radical ideal will give you the same set of points. So to illustrate it, see, suppose you take let's take a polynomial n equal to 2. So polynomial ring in 2 variables, and suppose I take the ideal generated by x1 square. This is ideal. So what will be the picture there? Now the picture I have to draw in K2. K2 is a plane, a fine plane. And what will be the picture for, that means x1 square is 0. But x1 square is 0 means that is this. But line twice, but the picture is same. So this is x1 equal to 0, that is x2 axis, or same as, this is same as x2 x1 square is 0, or more generally all this is same as, picture will look same, but what we are losing something, we are losing multiplicities. So when you go from algebra to geometry, something is getting lost. This information is getting lost, that this is double line. So this is very important, and this will cause also a lot of concern later. First of all, note that not every subset is in the image of Vk. So for example, if k is infinite and n equal to 1, and suppose so now what we have to do, we have k here and these ideals in radical ideals in the polynomial ring in one variable. Now if I take infinitely many points here, k is infinite field, so if I take infinite subset, if I take W to be infinite, it cannot be V of an ideal, V of any ideal A cannot be this W, because ideals here, ideals in these are principal. So they are generated by one polynomial. So therefore ideal is generated by one polynomial only f, and this Vk will be Vk of f. That means the zero set of the one polynomial in one variable, and that we know it is a finite set, and therefore it cannot be dW. Therefore all subsets are not in the image. So when we are hoping that this is a bijective map, that is not correct. So we have to adjust it. So we have to see which subsets come into the image. For that I want to define a map in the other way. So for this we define the map now in the other way. So I want to define a map which will be called Ik. This map will be from the power set of k power n to radical ideals of the ring k x1 to xn. And what is the map? the map is take any subset W and map it to, now I want an ideal. So that is IKW is by definition, this is by definition all those polynomials f in k x1 to xn such that f on any a is 0 for all a in W. All those polynomials which vanish on every element of W, you put it together. Now you check that this IKW is an ideal in k x1 to xn. Not only ideal, it's a radical ideal. Why that? Because what do you have to check? If I have two polynomials here, then the sum and difference is also there, but that is clear because if f of a is 0, g of a is 0, then f plus g at evaluated at a is same thing as fa plus ga or fa minus ga, and both are 0, therefore it is a subgroup. Then you have to check that if I have another polynomial, arbitrary polynomial h in n variable, and if h times f is also there, because h times f evaluated at any a in W is ha times fa, but fa is 0, therefore, so it's clearly an ideal. Also similarly, it is a radical ideal. If f is there, that means f of a is 0 for all a in W. So if somebody is in the radical, then the power will be here, but then the power fn a is 0, then f of a is 0. So therefore it is a radical ideal. So we have defined therefore a map from a power set of Kn to power set of other to the radical ideals of this. Now the big question is I want to say that this Ik and Vk, what is the relation between the maps Ik and Vk? And that was given by the strong null standards. So this is Hilbert's strong null standards. That says that if I take any ideal A and then take Vk and apply Ik, then I get back A. This is, therefore that means what? That means these Ik and Vk, they are inverses of each other. On what? On, so Vk on the image of Vk. So Vk is a map from radical ideals of k x1 to xn to the image. I want to take only the image of it. So these are called affine k algebraic set. What is an affine k algebraic set? It is of the form Vk of some ideal. So this is also denoted by AFF k power n. These are affine algebraic sets in k power n. This is a subset of power set of k power n. So what are these? By definition, these are precisely, so an affine algebraic set is precisely Vk of some ideal A, where A I can assume to be radical ideal. So this map has the inverse, namely Ik. But that is under the assumption, this is under the assumption that K is algebraically closed. This was proved by Hilbert in 1863. So that gave a way to study affine algebraic sets in k power n with the help of radical ideals. So therefore, from that onwards, study of ideals in a polynomial ring, maximal ideals, etc., that became very, very important, because that corresponding to study of this geometry. This geometry is called affine algebraic geometry. That study is now equivalent to studying ideals in a polynomial ring. In the polynomial ring kx1 to xn. So this gave a two-way traffic, because when you want to study ideal, then you study corresponding and then so on. So that became this is known as classical algebraic geometry. But then remember this has a big assumption, K is algebraically closed. So for example, one cannot study real algebraic geometry with this. We need a different tool for that. Alright, so this was what the motivation for Hilbert-Null-Standards, which deduce Hilbert-Null-Standards from the normalization lemma. Normalization lemma is more general. And now in the remaining time, I want to now generalize this also. So remember, to each, suppose I have a field K, what we understand from this study is for a field and for R, where R is a K algebra of finite type. To study this, we have attached a set to this, that is K spectrum, K spec R. K spec R is by definition home K algebras from R to K. And this also you could identify with the maximal ideals M in SPMR such that the residue field R by M is K. This is the K spectrum. This is obviously a subset of the maximal ideals. And we have seen example, there are maximal ideals which are not here. For example, when K is real numbers, then x square plus 1, which is a maximal ideal generated by x square plus 1 is a maximal ideal, but it is not K spectrum. It is not in the K spectrum. And this is further enlarged to spec of R. This is the set of all prime ideals. The set of all ideals in R. Now we have only defined a topology here, and that too we had an assumption that this K is R is K algebra of finite type. So in general we don't have K field, a ring may not contain a field and they may not be finite type or field, and so that we want to define more generally a topology on this bigger set, on the spectrum set, and therefore I can take induced topology here. This is not there. So more generally, what do we have for any ring R? If R is any commutative ring, we have these two sets, SPMR, which is contained in the spec of R. And we know this set is non-empty when R is non-zero. This is under the assumption that R is non-zero. This is what known as Krull's theorem. Krull's theorem says that if you have a non-zero commutative ring, then there is at least one maximal ideal in R, and this was proved by using Zorn's lemma. And therefore, there is a prime ideal. There may be many prime ideals. So we want to now define a topology on, we want to define topology on this bigger set, spec of R. So that means what we want to define, we want to give you a collection of subsets of this which satisfy properties of the closed set in a topological space. That means we want to give a collection which has empty set, which has a whole space, and which is closed under arbitrary intersection, and which is closed under finite union. If I have such a collection, then that will define a topology on that set, and these sets, these collection elements of this collection will be precisely the closed sets in that topology. So, we are looking for a collection of, so we are looking for a subset of the power set of the spectrum. Okay, and what is that now? I will now define. So, obviously the ideals will come to the help. So, take any ideals in arbitrary in the ring R, and I want to define a map from this to the power set of spec of R, and this map I have called it V. So, take any ideal A, and now I want to define V of A, and what is V of A should be a subset of a spec of R. So, what is this by definition? This is by definition all those prime ideals P in spec R such that P should contain the given ideal A. So, I have defined V of A. Now, there is no suffix k here because there is no field. Now, first of all, this ideal V of A and V of radical of A, they are same, because if P contains A, then P will also contain radical of A because P is a prime ideal. Recall that radical of an ideal is by definition all those elements F in the ring R such that F power n belongs to A for some n. So, this is the radical, and in general radical of the ideal contains A. If it equality holds here, then one calls that ideal A to be radical ideal. So, because this map ideal A and radical of ideal A, they go to the same set. So, we will concentrate on the radical ideals only. So, we therefore think V is a map from radical ideals in R to the power set of the spectrum. A going to V of A. Now, again we only consider the image of V and then try to define a map. We would try to define a map in the other direction, that is will be map I. So, what is it? We have given any subset Y of the spectrum and we want to define I of Y. I of Y is by definition, you look at all those prime ideals in Y, so intersection P varies in Y. So, therefore, this makes sense. This is an ideal. Not only it is an ideal, it is intersection of ideals and intersection of radical ideals. Therefore, it is again a radical ideal. So, this indeed belongs to the radical ideals in R. And now, like we have checked the properties of this V, what are the properties we should check? We should check, so this is a proposition. This will check that the collection V of A, where A varies in the radical ideals of R, this collection satisfy the properties of closed sets in a topology. What does that mean? That is 1 V of 1 is empty set, V of 0 is whole spectrum. So that means the whole space is there, empty set is there. Second, we have to check that it is union of V of some ideal arbitrary family. This is intersection of V of AIs. So that means given V of AIs, a family V of AIs indexed by I, then their intersection is also of the same form. And third one, that if I take the product ideal A times B, which is same thing as intersection ideal, which is a union of A and V of A union V of B. So this is also easy to check that. See, if you translate it, what do you want to prove? It is very easy. This means if a prime ideal contains the product of two ideals, then it contains either of them. So similarly, if prime ideal contains all these guys, then it belong to the intersection. So these are precisely the properties that closed sets satisfy in a topology. So therefore this topology, this defines a topology on spec of R and is called the Zariski topology. On R, on spec of R. All right, so one has to check these properties, but one possibility to check this, I want to give that notation. What are the open sets? So open sets are precisely the complements. Open sets in spec of R are precisely the spec of R minus V of A, Also these are called D of A. So what is this by definition? So all those prime ideals P in R such that P is not here, that means P does not contain A, then it is there. Right? So these are precisely the open sets. Now, what is V of A? Another important thing one should note here is that so when the ring is Noetherian, when R is Noetherian, then every ideal A in R is finitely generated. But then this V of A and V of a generating set are same, finitely generated. So that is A is generated by F1 to Fr. Then V of A is same thing as V of F1 to Fr, and therefore we only have to consider finitely many elements at a time. No? So therefore what will be the complement of this? So D of A, which is spec R minus V of F1 to Fr. So these are precisely all those prime ideals P in R such that P is not here, that means at least one of the Fi is not in P. So, Fi is not in P for some I from 1 to R. So, for example, if what will be D of a single element F, this is spec of R minus V of F, which is all those prime ideals P such that F is not in P. So, these are the basic open sets. So, therefore, what we noted is this collection DF, where F is in R, is form basic open sets for the Zariski topology. On spectrum. All right. So, to check things, the following notation is very useful. So, let me write that. Let me explain how does one write neatly. So, first of all, for psychological reasons, one like to have a notation for a topological space to be capital X. So, given a ring here R, I have this spec R, this is a set of all prime ideals. This I would like to denote this by X, because we are used to topological space by capital letter X. Okay. So, and how are we going to change our notation? When we want to stress upon the properties of prime ideals, then we will write the notation P. And when you want to set stress about the points in a topological space, then I will write it X. But just to keep track, this P corresponds to this X, I will write P suffix X. Just to remember that this P we have identified with that X. Alright, now therefore in this notation, okay, so I have the ring R here, I have R by Px here. Now this I have performed the algebraic operation, therefore I want to write it as Px. So this is a residue map, this is modulo Px map, this is integral domain, and therefore it has a quotient field. So quotient field of R by Px. This quotient field I want to denote by kappa x, because it depends only on x. X means Px. So this is a field, this is a field, and we have a natural map here. See, this is a ring homomorphism, this is also ring homomorphism, because this is embedding of the integral domain in a quotient field. Now, if I have an element F here, I denote the in general elements of the ring by letters F, G, etc., like we denote the polynomials, because I always want to think rings as polynomial rings, and therefore the choice of notation is from that implication. So F goes to F bar here by reading mod Px, and this F bar will go to somebody here. That image I am going to denote by F of x. This is the image of F in this quotient field. It comes F bar and then this. Now, this is a ring homomorphism. This is a ring homomorphism means what? If I take F and another element G, F of G, and take its image directly, or I take the image of F and image of G, and then this is equal to this plus this, because it is a ring homomorphism. Similarly, F times G evaluated at x, I will write it evaluated at x. This is Fx times Gx. So if this product is 0, then one of them has to be 0 because we are in images are in the field. So therefore, what will be my definition of V of A? Now let us, for example, V of F will be what? These are all those prime ideals P such that P contains F. That means F belongs to P. So this is the same thing if I want to write in the new notation now. These are all those elements X in X. Remember this Px we have identified with X such that now this will be what? F belong to Px. So that means F of X is 0. This is the image of F in the residue field Kx. So therefore this gives the same feeling as what we did it for K spectrum, and therefore if you adopt the same checking it will be very easy. So I suggest you adopt for checking that they satisfy the properties of the closed set, use this notation, it will be very, very helpful. This notation was due to Grothendieck. Grothendieck is the one who changed algebraic geometry to very abstract algebraic geometry, and it gave lot of important results. With this he proved lot of important results. Okay, so with this I will stop.